Hello, friends. Excited to spend a little bit of time with you today. Let's go ahead and get the screen shared and we'll get started. So the first thing that I wanted to talk to you about was the homework 6. We've got a few problems to work through. One of the things that I want to point out was this homework is completely bonus points. I made a mistake when I was loading these in, and so you don't have to do these if you don't want to. All right, so let's take a look at these. All right, let's go ahead and get some of the resources opened up. So we'll open the syllabus because the syllabus has the Google Doc. The Google Doc has several things. So here's the spring 21 questions. And the question we're looking for is 6.1, 8, and 9. So let's drop down here, 6.1, 8, and 9. How many different three-letter initials with none of the letters repeated can people have? Okay. So this is one where you can work through it. So there's A, B, oh, hey, hold on just a second, friends. I'm going to stop my share and I'm going to switch my camera. There we go. Make some adjustments here. Uh-oh, camera got put on upside down. All right, just have to flip it real quick. There we go. Sorry about that. Okay, so this would have no repeats. So this is the first letter, this is the second letter, this is the third letter. So we can have down to the 26th letter here. And so there's going to be something like 24 options. And then we can change B again. And so for each one of these, we'll have like 24 options. And so it's going to be, 200 times 200. I'm sorry, 20 times 20 is like, my math is not great today. 20 times 2 is going to be 4 times another 10 will be 400. So yeah, there's going to be quite a few. Well, anyway, let's see what they've got for a solution on 6.1 question number 8. So to do that, the Dropbox has a link to a student resources, but I've already got that downloaded. So here's the even questions. And we'll drop down to, there we go, 6.1, number 8. So it says there's 26 choices for the initial letter. So whatever we choose here, we can have 26. Then we'll have another 25 for the second letter, and then another 24. So my math was just a little bit wrong, but the final number is going to be, and by the way, you can't really see what's on my screen right now. So you're not here to tell me that. So I'll share screen 4. Yeah, and here's the question number 8. Okay, so now that we've got that out of the way, let's go look for what the other question is. So 6.1, question 9, three-letter initials are there that begin with an A? Okay, so I'm going to stop my share. And it's how many different three-letter initials are there that start with an A? So on this one, it can be A and anything of the 26 letters and anything of the 26 letters. So 26 times 26, let's math that out right quick. 6 times 6 is going to be 36. Carry the 3. 12, 15, 0. That's 2. Carry the 1. 2 times 2 is 4. 5. Add 6. 7. 676. Well, sure. Why not? Right? Let's go see if we can verify that. So this one I don't like as much because it takes me a while to skim through it and find what I'm looking for. So 676, 676. So hopefully that makes sense on how you burn through that. Okay. Now let's bop over back to here. Whoops, swing and a miss. There's the right one. Okay, so now we're moving on to section 6.2. So let's take a look at what 6.2 has in store for us. So let's go over to the questions. Share my screen again. It's actually dangerous having that up there. Okay, so we're going to now look at 6.2 and see what that has to do. Oh, by the way, just so we're all on the same page. 676 was A, and then 24 letters, 26 letters for the second one, and 26 letters for the third one, because it doesn't say we can't have repeats. Okay, sorry about that. Now, moving back, we're going to go on to 6.2, 3, and 4. 6.2, 3, and 4. Okay, so 6.2, 3, and 4. It says a drawer contains a dozen brown socks. So 12 brown and 12 black. Unmatched. A man takes socks out at randoms in the dark. That's sexist. How many socks must he take out to be sure that he has at least 2 socks of the same color? Okay. See, that's an interesting question. We're going to go and we're going to do question 4 first. All right. So question 4, we've got 10 red and 10 blue. So at least 3, same. And that's A. And B is going to be at least 3 blue. Okay, the reason I like to do the even ones first is they usually have a better explanation. So let's bop over 6.2. So here's the solution they have in 6.2. They say there are 2 colors. These are the pigeonholes. We want to know the least number of pigeonholes needed to ensure that at least one of the pigeonholes contains 3 pigeons. By the generalized pigeonhole principle, you are so welcome. The answer is 5. If the balls are selected, at least, so for A, it says 5 over 2 must have, which equals 3, same color. On the other hand, 4 balls is not enough because 2 might be red and 2 might be blue. Okay, note that the number of balls was irrelevant, assuming it was at least 5. Okay, so that makes sense. If we do 4, we might be red, red, and blue, blue. Here, let me go ahead and stop my share right quick so you can see this a little better. It might be like that. So there's a possibility that it didn't come out. But if you do 5, it has to be, it might be red, blue, 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 or it could be red, red, blue, 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 or it could be red, 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 blue, blue, or it could be red, 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 blue. But notice how there's at least 3 of this flavor, 3 of this flavor, there's 3 of this flavor, there's 3 of this flavor. So basically, draw 5, get 3. Okay, now that we've got that, now we can circle back and we can go ask the question, if we're getting brown socks, let me share my screen again. Okay. No, yeah, that's okay because we'll need this 3 in just in a little bit. Okay, a drawer contains socks. How many socks must you take out to be sure that you have at least 2 socks the same color? Well, let's say that you grab 1 sock. Maybe it's black. BL or BR. Definitely can't have 2 there. So what if we draw 2? Well, maybe you have black, black, or you have black, brown, or brown, brown, right? There's a possibility that you've got 2, but you've also got a possibility of just getting 1. Stop my share right quick so you can see that easier. All right, so if we do 3, it's either all black, so 3 BL, or it's 1 and 2, or 2 and 1, or 3 brown. But every case, you're going to have at least 2 of the same color. So as long as you pull 3, you should have a sufficient case. Okay, share my screen again. Part B. It says, how many balls must you select to be sure of having at least 3 blue balls? Okay, now that is a significantly different question. So we've got 10 red and 10 blue, and you want 3 blue. Okay, so let's go see what they have in store for us there. All right, so this time it says she needs to select 13 balls in order to ensure at least 3 blue ones. If she does not do so, then at most 10 of them are red, so at least 3 are blue. On the other hand, if she selects 12 or fewer, 10 of them could still be red, and she might not get her 3 blue balls. So this time the number of balls did matter. Okay, so basically, if you're going to draw 13 balls, there's no way that you can do it. You could say, your first 10 draws were reds. Well, you're still guaranteed to have 3 blues. So the answer is you need to draw 13. Okay, now let's go back and let's visit 6.2 problem 3 again. It says, how many socks must you take out to be sure that at least 2 black socks? Okay, so we need 2 black and then have 12 brown and 12 black. I'll stop my screen. All right, so let's math this out right quick. You need 14 socks because 12 could be brown, but you can't get to that without at least 2 black. So you're guaranteed, if you draw 14 socks, you're going to grab 2. Okay, so share my screen and let's continue on. Oh, let's verify that right quick. Here we go. So 6. Oh, no, that was the one I wanted. Just got to go here. 6.2, yep, 3 and 14. Yay, so we got those correct. All right, now need to go, yep, that's the right one. 6.3, questions 8 and 9. All right, so questions 8 and 9. How many different orders can 5 runners finish a race if no ties are allowed? Okay, so this is a permutation question. So we've got 5 runners. We've got no ties. Okay. Well, let's just, so 1, 2, 3, 4, 5. 1, 2, I'll stop my share. 1, 2, 3, 5, 4. 1, 2, 4, 3, 5. 4, 5, 3. 1, 2, 5. 3, 4. 1, 2, 5, 4, 3. 1, 3. And then 2, 4, 5. 2, 5, 4. And then 1, 3, 4. 2, 5. 1, 3, 4, 5, 2. 1, 3, 5. 2, 4. 1, 3, 5, 4, 2. And these are just permutations, right? We're up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've done a dozen of these permutations, and that's what they're talking about in this scenario. Okay, so let's go ahead, share our screen again. So the question is, how many different orders can 5 runners finish if no ties are allowed? So order does matter in this one. So let's pop over this one, I do believe. So there's 5 permutations. And so, all right. So for this one, I'm going to go ahead and open up a different resource. There we go. Oh, wrong tab. And this is 6. And this is permutations and combinations. Okay. Example. How many ways can we select 3 students from a group of 5? No. A first prize winner, 100? No. Eight different cities. There we go. She must begin her trip at a specific city. Can visit any of the other 7. How many possible orders? Okay, so this one is now going to be 7 factorial. Okay, so example 6 is basically the same question. Here's another permutation question. And so this is just going to be 5 factorial, which is equal 5 times 4 times 3 times 2 times 1, which is, let's do 20 times 6 equals 120. All right. And just to verify, yep, 5 factorial, which is 120. All right, let's bounce back to the question. Oops. Yeah, this question right quick. The second question is question 9. So it says, how many possibilities are there for the win, first place and second, first, second, and third in a horse race with 12 races if all orders of finishes are possible? So in this case, on number 9, we've got 12 horses. And it says, pick 3. Okay, so now let's go back to the book. There we go. 8 runners in a race. The winner receives. How many different ways are to award these medals? All outcomes can occur and there are no ties. So this is 8, pick 3. All right. So P of 8 comma 3, ours is going to be P of 12 comma 3. Now let's go find out how to calculate that. Well, okay. So this is going to be 12 times 11 times 10. So stacking this up, 12 times 11 is going to be 2, 1, 0, 1, 2, plus, so 132. Okay, so I say 1320 is the answer. So this is 6.3, question number 9. So let's bounce down, see if our 6.3, question number 9, 1320. So we've got 12 ways that we can pick the first horse, but with that, we'd only have 11 ways that we could pick the horse that came in second. And if we've picked the first and the second horse, there's only 10 remaining ways that we can pick the third horse. So 12, so it's going to be 12 times 11 times 10, which is where we get the 1320 from. Okay. Now, bounce back here. And now we're going to skip ahead to chapter 6, section 6, questions 5 and 6. So 6.6, 5 and 6. It says, find the next larger permutation in lexicographical order. Okay, so lexicographical order. So if we have 1, 4, 3, 2, all right. These often make my brain hurt a little bit. It's basically the bigger number. Let's pop into the book and see if they have any examples on permutations. Okay, so the permutation 23415 precedes 23514. So 415 is before 514 because these agree in the first two positions, but the number in the third position in the first is 4 is smaller, so this is the smaller one. So this precedes this. Okay. Following a given permutation. So this, suppose in interchange in and in to obtain a larger permutation. No other permutation is both larger than the original permutation and smaller than okay, so 432. The one that's going to be bigger is going to have a 2 here. So maybe it's 2, 4, 3, 1. Or is it going to be 2, 1, 3, 4? I think it should be 2, 3, 2, 1, 3, 4. Basically, the idea is, okay, take this is the 1 is the only number that hasn't been shuffled because it should go like 1, 2, 3, 4 in that order. But now it's 1, 4, 3, 2. You can't switch any of these out for a bigger number. Like the only way to make this bigger is that you have to switch out this one. And so to make it a 2 and then 1, 3, 4. Let's go find out if that's right. So that was 5A. So we'll pop in here. We're down to 6.6. This is number 5A, and I was right. It's 2, 1, 3, 4. Okay, now these are, let's do B right quick. It's 5, 4. It's going to be 5, 4, 1, 2, 3. Okay, so the next one we can get away with is 5, 4, 1, 3, 2. We just take the last two numbers here at the end and switch them. Let's go verify that for B. 5, 4, 1, 3, 2. Yep, we just switched these last two around. Okay. Now we're going to do part C. And part C is 1, 2, 4, 5, 3. And for 1, 2, 4, 5, 3, we're going to have, we can switch these two. So 1, 2, 5, because if we switch the last two, it'll be smaller. So we'll switch the middle two. 5, 3, 4. So we have to kind of do a rotation of the last three. 1, 2, 5, 3, 4 for part C. 1, 2, 5, 3, 4. See, we yeah. All right, good. Now let's take a look at D. D is going to be 4, 5, 2, 3, 1. Well, we can't switch the 1 and the 2 because that would make it smaller, but we can switch the 3 and the 2. And actually, we can do easier than that. We can do 4, 5, and then make this 3, 1, 2. So we'll kind of shift around the last three. 4, 5, 3, 1, 2. 4, 5, 3, 1, 2. Very cool. And then finally, E, 6, 7, 1, 4, 2, 3, 5. Okay, we can just take the last two numbers and we can switch the last two numbers. So 6, 7, 1, 4, 2, 5, 3. 2, 5, 3 is bigger than 2, 3, 5. But there's no way to get a smaller one in between. Because if you get a smaller number in there, you'd have to switch something else that would cause problems. So it's 6, 7, 1, 4, 2, 5, 3. Go verify that part E. Oh, those cheeky little monkeys. So 6, 7, 1, 4, 2, 5, 3. I feel pretty good about that, following the patterns that we've used. And then F is going to be 3, 1, 5, 3, 1, 5, 2, 8, 7, 6, 4. So if you switch the 6 and the 4, that would become smaller. You switch the 6 and the 7, that would become smaller. You switch the 4 and the 7, that becomes smaller. The 8 and the 7, that becomes smaller. But you can switch the 4 and the 2. So it's going to be 4. And then we'll have to reshuffle them. And so it'll be 2, 6, 7, 8. So, and then the next one after that would be 4, 2, 6, 8, 7, 4, 2, 7, 6, 8, 4, 2, 7, 8, 6. Right. And so this is just a fun party trick. It's not necessarily anything crucial to know, but when you're thinking about ordered pairs and things like this, it's an interesting conversation to have. Okay. Now, make sure that we're doing the right problem. 6.6, question number 6. Part A. So it's 1, 3, 4, 2. And for this one, we can switch these two. So it'll be 1 and then a 4. Now, 3, 2 or 2, 3, 2, 3 is going to be a smaller number. And so then the one after that would be 1, 4, 3, 2. So this is bigger, this is smaller. So 1, 4, 2, 3. Let's take a look at B while we're here. It's 5, 4, 1, 2, 3. And we can simply just take these last two and switch them. So 5, 4, 1, 3, 2. Okay, draw some boxes here to speed the process up. Part C is going to be 1, 3, 2, 4, 5. And so we can just take these last two and switch them. 1, 3, 2, 5, 4. And let's do D while we're here. It's going to be 6, 1, 2, 3, 4, 5. 6, 1, 2, 3, 5, 4. Just switch the last two. E. E looks like 1, 6, 2, 3, 5, 4, 7. 1, 6, 2, 3, 5, 7, 4. We can just switch the last two. And then 2, 3, 5, 8, 7, 4, 1, 6. 2, 3, 5, 8, 7, 4, 6, 1. So just switch the last two. And that's for part F. Okay, so let's go see if they have anything to add on that discussion. 6.6. So the last pair of integers can be switched. So it's 1, 4. Oh, I circled the wrong one. So it's 1, 4, 2, 3. Cool. B is 5, 4. What a sec. Oh, 5. Oh, 5, 4, 1, 2, 3. That doesn't make sense. Let's go look at that again. Find the next larger permutation in lexicographical order. 4, 5. Oh. So 4, 5. 3, 2, 1. I read the wrong problem. Okay, if you switch these two, it's a problem. Switch these two, it's a problem. These two. So you have to switch these two. So it's got to be 5, 4. No, I'm sorry. It can be, the first number has to be 5. So I'll write it up here. 5. And then it can be 1, 2, 3, 4. So we have to switch the 5 to the leading spot. That's the only switch we can make that's reasonable. Then we have to find the smallest number we can, and that's going to be 1, 2, 3, 4. All right, so I messed that one up. 5, 1, 2, 3, 4. So that matches with our logic. Okay, part C, 1, 3, 2, 5, 4. Yep, got it. 6, 1, 2, 3, 5, 4. Yep, got it. 7, 4. Yep, switch the last two. And 6, 1, switch the last two. Okay, so that is the homework for chapter 6. And again, it's not terribly bad homework, but because I messed up on the assignment, I decided I would just, instead of just telling everybody, hey, I moved the deadline up 10 days, I felt like that would be kind of a jerk thing to do. So instead, I said, hey, let's just make the whole thing bonus. And it's not that bad of an assignment. So anyway, I hope that helps. Thank you all for your time. Have a wonderful day.